What I have here in Desmos is the equation of a line, 2x plus 3y equals 7. And something that we know about this line is that every single point on it, well, something we know about any graph of an equation, is that every point on it is a point that satisfies, is an x and y coordinate point that satisfies the conditions set forth by the equation. For example, on this particular line, the point 2, 1 is on it. 2 comma 1. If you plugged in 2 for x and 1 for y, you would see that it would be true, right? 2 times 2 is 4, 3 times 1 is 3, 4 plus 3 is 7, and it works. And so what's interesting, though, is when you add in a second equation, it becomes now what we call a system of equations. We have two equations here. We have the second one is x equals 3y, and if we wanted to know what point on the coordinate system satisfies both equations at the same time, well, now we'd be solving a system of equations. And you can see graphically that there's only one point on the coordinate plane that satisfies both of the conditions set forth in both of these lines, and it's the intersection point. And Desmos is very convenient, and graphing calculators also are very convenient for finding the intersection point between two lines or two curves or two graphs, any kind of graph. And by the way, side note, if you're taking a standardized test and your standardized test permits the use of Desmos, which seems to be happening more and more often, at least here in the United States it is, you should absolutely 100% use Desmos to solve system of equation problems, because graphing, typing in the equation and then just looking where they intersect, by far the fastest way. There's a few exceptions to that, like there's two algebraic ways we have of finding the solution to systems of equation problems, and they are elimination and substitution, and we'll certainly talk a lot about both of those. But graphing is if you have a utility like this at your disposal, is by far the best way to do it. Now, there's limitations to graphing, because if I asked you to graph something by hand, it'd be very hard for you to precisely find that the intersection points are 2 1/3, and then I think this one is 7/9. Like, that's not on a nice little grid point, on your coordinate plane, even if you're using graph paper. And so we've developed these algebraic ways to compensate for that. But we can also talk more about how it's not just lines, system of equations with two linear systems that have solutions. We can also have, for example, a hyperbola and a line. So this is the black line here is a hyperbola, and the green line is the original line. It has two intersection points. Totally possible for us to calculate their intersection points, because here we just have two equations and two unknowns. Generally speaking, if we have two unknowns, all we need are two equations to solve a system like that. We can have not just lines, but we can have, for example, here's a line and an ellipse, a hyperbola and an ellipse, two conic sections. And two conic sections, in this case, they intersect 4 times. What if I had that original hyperbola and this parabola? Well, now there's two intersections there. And you can see that all sorts of combinations here, we have different coordinate points. And so what we're going to get into in this unit is calculating the solutions to systems of equations, not just plain basic plain basic equations, but also word problems or applications of systems of equations. We'll also talk about systems of equations with more than two variables. The most common one, and one that tends to be, it's a very tedious process mathematically, is a 3-variable system. But just like graphing is a really quick way to get the solution to 2-variable systems, there's a similar way that we can get, not a similar way, but there's also a kind of a shortcut type of way where we can get the solutions to systems of equations with more than 2 variables. In fact, many variables. And we'll get into that. That'll be kind of where we conclude this unit.